Thank you.
All right, everyone. Let's welcome back. Welcome back. How? Like everyone's like still on vacation. I'm still kind of in vacation mode. I'm having some issue with Slack, so the live stream URL is just up there. YouTube for Violet Live. Yay! It's not too bad. How's everyone doing? How's your vacation? Did you get a ton of work done on Capstone? No? That's okay. Yes is also good. All right, let's talk about functional programming. What is functional programming?
I could be wrong, but I think it's Thomas Linder's name. It's like programming based on like what components expect to receive, like what they're handing around, and that's what you're focused on versus the algorithm. Like you start first based on the structure of how things will move.
Yeah, so it's and the pieces of our programs that that like take and receive things are functions. So another way of saying that is it's like programming based on functions, which is true. And we're like particularly concerned with their signatures, so like how they map their input to output. And the reason we're concerned about that is that in functional programming, ideally, your functions are pure. Should say pure functions, meaning they don't have side effects. Meaning, so no side effects, and that means that for a given input, we always get the same output. Oh, that seems wrong. For all x, y is stable for all x, y, which means that we can, for example, we can memoize functions. Because they don't, you know that if you capture their input and their output, then it's always going to be the same. Which, there's an interesting cone here, which is how, okay, sure, that's great, but everything a program actually does is a side effect, right? Like printing something to the screen is a side effect. Whatever function prints something, you can't take that back. It's like done after it's printed. So how do you represent side effects in a system like this? Yeah, basically. So how do we handle side effects? So the way this is handled like formally is called a monad, but basically, like, how would we implement console log? Like this console log does not have a return type in JavaScript, right? It returns like in classic JS. Console log takes a pattern and returns undefined with side effects. A pure console log would have a signature something like pattern, but then it returns effects, or it like returns maybe in particular IO effects. So however it is you represent what the side effects of something should be, often by like putting a function in there, pure functions will return any side effects they should have. Yeah? Damn it. What's it saying?
It's just pause.
I don't know what to do about this. I'll have a recording that I can upload later. Sorry. Okay, cool. What else? What are some other patterns we see in functional programming? Because we see, like, there are languages that are, like, really concerned about, like, being, like, pure functional programming languages. Like, Haskell and Elm use patterns like this. In order to perform anything with side effects, like, you have to sort of pass around, you have to, like, collect these effects and join them up and, like, pass them around somehow. JavaScript, of course, does not make us do this, which, you know, there's pros and cons to that, right? In JavaScript, you don't necessarily know, calling a function, whether it's pure or whether you can capture the results. You basically don't know if it has side effects or if it's deterministic. Whereas in those languages you do, but in those languages you have it's kind of a significant pain point to print something or perform I/O, because for actually in a similar way that asynchronous operations can be a little bit painful in JavaScript, in those languages, any operation that might change the state of the world, you have to handle kind of like an asynchronous operation, which can be irritating. But we still in JavaScript use patterns from functional programming all over the place. So one thing we use a lot, of course, is recursion. And maybe we don't actually use it that much in JavaScript, but in some, in most even, I'll say, functional programming languages, all loops are recursion. So instead of, I mean, these languages also usually have a construct that lets you be like, for x in some list, do something. But that gets turned into a function that takes a list and you see this pattern a lot. Here's the first thing, here's the rest of the things. So we're going to do something, like finally actually do something to the first thing, and then do something to the rest. So this is the general, sort of the general way that you loop over a whole bunch of things without using a loop, right? And in JavaScript, we wouldn't do this. This would actually be a terrible way to loop over all things. And why is that?
Like, does it? Oh, yeah.
Like, let's sort of concretize this by saying we'll take this action and apply it to the whole thing. So this becomes action, and then this becomes this. Okay. Yeah.
Doesn't it require that you go like through the entire rest object in the array first before you can actually do the action?
Yeah, so there is, this is going to make a copy in some sense. Like this is certainly going to require that we create a new list, and spreading this is going to require that we iterate over all n things. So yeah, that's one reason we want to do it in JavaScript, because this involves a lot more copying. But we could pick a different data structure than an array to do this, right? In fact, if we use linked lists, it starts to feel a lot better. So let's say that I have, here's what a linked list looks like. I'll say I've got a list node, and it's got some data of some type, and then a next list node. I'm kind of making up syntax here, but let's pretend this is how we can define a type. So now if we're operating on things of this type, then so I'm going to take an action, and I'm going to take a list node. So here, action will be something, we'll get to that. So action will here be something that takes T and returns U. So this is saying we're going to apply some function that this is map. I should just call this map, right? Because this is going to take each thing in our list and turn it into a different thing by running it through the mapper. So if we're using a linked list to do this, then it starts to make a little bit more sense, right? Because I can say, I'm going to return a new list node. Let's pretend that the obvious constructor exists here. Mapper of list, and then what's the next thing? It'll be, this is returning a list node, so we can just call map on the rest. List.next. So this is kind of nice, right? It's like kind of a, it's one of those like delightfully recursive, feels almost like magic functions, and a lot of functional programming is delightfully recursive and feels almost like magic, where we end up iterating through the whole thing because we're calling it on, like here we're calling it on the first item, this should be list.data, and then here we call it on the whole rest of the list just by passing in the next item, the next list node. In functional programming languages, a list node is often called a const cell, and there's funny names for data and next. It's like CDR and CAR. I don't know why. I just don't know why they're called that. So that gets rid of this copy, right? Now we're just making new const cells for each item in the list, which is sort of the minimum thing we can do. But there's still a problem with doing this in JS. How many times can we recurse? Like I guess, let me ask a different question. What happens when we call map of list.next? What's that? Oh yeah, maybe we should be like, if not list, return null. Sure. Okay. But what happens if, so now we know what happens if there's no next, but what happens each time, like for each item, when we encountered this function call? Or any function call. Yeah, so we're going to, if I call map of, let's see, x becomes x plus 1, I'm going to write this as a list because, or as an array because it's easier, but pretend that, here actually, why don't I just, here. We have a pretend list constructor that takes a bunch of things and returns the first list node. So this is going to first call, so this is the first call, and then we're going to say that, okay, we have a list, so we're going to return a new list, basically, of the first data item. So we get to return new const cell of 2, and then list of, oops, and then we call map recursively, right? Map of 2, 3. And we can't actually return, right? We can't construct this cell until this map has returned, so it goes on the stack. So here's what we're doing. And we're specifically evaluating this part of it. And in order to get this value, we have to add something to the stack. And then same thing happens. A new const cell of 3. And then we end up with the last thing on here. List of 3, return new const cell of... Now it's an empty list, which is null, because the next item in this linked list will be null or undefined, which means that now we get to the base case. And so that hits this. And then it returns all the way back, and we end up constructing the list. So we pop this, and then we pop this, and then we pop this, and then finally we end up with a list of 2, 3, 4. So that's great. We got the right answer. Maybe I could put in some print statements, and we could actually run this. But every time, basically for each item in the list, we had to push a new stack frame, which is not totally ideal because in JavaScript, you can only push so many stack frames. Like the stack is actually right at the end of the heap or something, and it only has enough space for about like 65,000-ish stack frames before it hits the end of the stack, literally the end of the space allocated to it, and your program crashes. Which means we have now limited ourselves to processing lists that are like no more than 65,000 things, which is not that big, right? Like we can actually process much larger data structures than that in our computers. So what most functional programming languages do is they say like, okay, we can rewrite this to not require that you wait for this return value, right? We don't really need to wait for that in a certain sense, because if the recursive call is the very last thing you do, if we can somehow write our function to take, to like return, this is not what you would do, but to return the recursive call itself so that you don't have anything left to do after this function returns, then now you don't need to like stack up function calls, and you can just replace the item on the stack with the next call. So we could rewrite our function to be, and the proper term for this is tail recursive. Tail map. And how do we do that? We basically need to have already constructed this cell. We need to have like done this new const before calling map. So maybe we say that this takes an output list. And now we can say, here's our output. It's got, it has this data. Oops. And we can attach this cell to the list, so we can say that prev.next equals output. And so now if we call map, I might have to change what we return here. Oh yeah, if not list, return previous. So now if we call map and pass in, let's see, the mapper, and then output, and then list.next, now this is tail recursive. Now the last thing we're doing, oops, I should say tail map. The last thing we're doing is making our recursive call, which means there's nothing left to store out of this function. We don't need to like keep the stack frame around at all. So we can just replace our position on the call stack with this next one, which looks a lot more like doing a typical list, right? Like there like kind of is a function call involved, but like it's tail recursive. So like our current state is just not important anymore. And so this is a technique that's that a lot of functional programming languages will actually like apply to your code for you and guarantee that if your function can be expressed in this way, it will be, so that you can process data structures, ideally recursive data structures like linked lists, without incurring this like penalty or this like weird behavior in the case of really large data structures. This is also something that JavaScript is adding eventually. Like right now, I don't think it's the case that if you rewrite your function like this, it will be guaranteed to not put things on the call stack. But that is like in the spec at some point that JS will basically treat tail recursive functions specially and not push to the call stack in this case. Okay, cool. So recursion in both functions and data structures, major functional programming thing because it lets us articulate like all the operations we're doing kind of mathematically, like right? Like here we're sort of saying what is the mapping of this function to this list? Well, it's a list that maps one piece of data and then the rest of the data. Questions about that? I know the answer is probably yes, but the question is like so deeply buried in the sea of confusion. Okay, let's talk about, let's see, what should we talk about next? We talked about recursion. Oh, let's talk about higher order functions. These are another functional programming technique that we see a lot of in JavaScript and actually especially in React. So what's a higher order function? Yeah, so it's some function that takes some function and returns another function. So an example of this, oh, what's a good example of this? I mean, every higher order component is actually a higher order function, right? So like connect takes, oh, what does connect take? Map state to props, which is a function mapping, well, state to props. That's kind of not a very interesting signature. Map dispatch, which takes what? It takes the dispatch function, which takes an action and returns nothing, and then returns props again. And then it takes a component, which is itself a function, and it returns a new component. Another example from the React world, or in this case the Redux world, is Redux middleware. So connect, an example. Redux middleware is also a higher order function. And the way I remember how to write middleware, should you ever find yourself needing to write it, is that it's a function that takes a store. I'm going to write it like this. And it returns, oh god, it takes a store, it takes the store's current dispatch function, and returns a new dispatch function, which, when you write it out in JS, you can write it like this. And then you can, do something here when an action is dispatched. And so from that, we can sort of imagine how apply middleware works. If you have a bunch of functions that look like this, you can compose them in sort of this slightly special way where you pass the last function to the second to last function, and then you pass that return value to the third to last function all the way down until you finally get a new dispatch function for the entire store. And that's what middleware does. So this gives us actually a lot of flexibility, right? Even we're sort of providing an interface that gives us a lot of access points. Like, I can do something to the store. If I want to subscribe to the store, I can do it. Subscribe, blah, 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 do something. I don't know what my middleware is doing. If I want to do something at the moment when my middleware is initialized, so once I have the next dispatch function, I can do that here. Now apply middleware has been called. So we can access next, which is the next dispatch function. Sometimes I also call this dispatch, store next action, store dispatch action. They both sound nice. And then finally, we get this point where we can change what happens when an action is dispatched. Another place we see higher order functions, or one place I like to use them, that I think I've seen many of you using them, is inside of event listeners. So, or specifically to create event listeners. So if I have my classic form element, is this gonna be crazy? Let's do this as a class. Pool form extends React component. When I render, so I've got an input in here too on change. This dot should, I'll just say on change of. Let's give this a name, or not give this a name. Oh, this is tricky. I'm realizing that I wouldn't use a higher order function here, but I'm going to anyway. So let's say that this is my name. Great. So now onChange is a function that takes a field name and then takes an event and says this dot set state field name to be event.value. Does this make sense to everyone? Has everyone seen something like this? So this has one significant downside, which is that every time we render, we're creating a new function. Which we sort of create functions left and right and don't think about it very much, but it's not free, right? We have to call this function for one thing, and functions take 36 bytes of memory at a minimum, so that's not super great. None of these are killers. Oh, let's have a non-submit as well. Default, and then let's pretend that this is how it works. By cool form, just expect to non-submit prod. So one thing we could do to fix this is we could memoize onChange. So onChange is within the context of a single instance, it is a pure function, right? So given a particular field name, it'll always return a function that does the same thing. So we could memoize it. And a way that I might like to memoize it is to write a memoize higher order function. And how would that work? How would that work? That's going to take a function and return the memoized form of it. And so first we should have a memo. So let's say I'm using a map to store a mapping between arguments and values. And so whenever, I'm going to return a new function, which takes all the arguments that this function could possibly take, and says if they are in the memo as args, return memo.get args. Otherwise, I think I have to do it like this. In fact, I should change the sense of this. If it doesn't have args, then memo.set args func of args, and then always return what's stored in the cache. So maybe calling this the cache is better. So now for a given field name, we are only going to call this, underlying function once, which means we're only going to create one underlying function. Okay. Let's talk about one more functional design pattern, which we're, I think, going to see tomorrow. And we've kind of seen it all over the place here, where in order to do something in a functional programming world, you generally would not extend a given data type, but rather you would create a new data type that composes, that includes within itself the data type that you want to extend. So that's this principle of composition over inheritance. And let me think of a good example for that. Like, well, for example, could we redefine the component interface to not use extension? That's a little bit tricky, right? Because we actually want these to do certain things. But okay, let's try it. We can do it, right? So if we weren't going to extend React component, we might say that a component just can be an object with like its lifecycle method. So here's did mount and render, and most notably some like should component render, and basically all of the things that React needs to be able to do to an element in order to figure out like how it should be rendered. All of these things like now have to be implemented by this object, which is like, this is the downside of composition, right? You can end up with a lot of boilerplate. But we could fix that by having a function that goes and says like as component of some object. And then this, of course, is a function. Everything's a function that takes an object and is like, if not object.should component render, then object.should component render is some base component.should component render. In fact, I could just say react.component.should component render. And if I do this for all of the lifecycle methods, basically I can provide default values and at the very end, of course, return object. So now, like creating a component looks a little bit more like this, where I can be like render, you know, return hi. Obviously, you wouldn't use a smart component for something just like this, so maybe component did mount the subset state. Greeting hello. And in JS, this looks kind of weird, right? Like syntactically, JS kind of wants us to use classes and inheritance for this, because this is it's like a little bit ugly, right? But other languages make different syntactic assumptions, right? And they make this form the pretty one. And even in JS, there's some value to this, right? Because when I define a class, I don't really get a lot of choice around what these things mean, right? When I like use this syntax to define a method, I'm always going to just like get a method on the prototype of this constructor. Whereas here, I can really do anything I want with these functions, right? As component can go and apply, what's a good example here? I can make some of these getters. I can apply a function to these functions before I put them on the component. So for example, I could do like, I could have another version of as component, which is as connected component, that now takes other stuff, right? Like map state and map dispatch. And then my as connected component generator could define all of these things a little differently, which might actually be better, right? Like right now, there's kind of some weird edge cases if you, because connect implements should component render, but then implements it in such a way that if you're receiving like props from the router, it's not necessarily going to render if you don't wrap the whole thing, if you don't make sure basically that those are sent in as props from the outside rather than from the inside. So I'm talking about this problem. It's like you can't connect with router, but you can with router connect. Because with router sort of injects props into X, which connect doesn't know about. But using something like this, we could figure out like, oh, this inner component is actually going to get some context, and I should handle it differently. Okay. Any questions? Anything you've heard about from functional programming that you would like me to talk about that I have not? Okay, we're gonna have a whole week of these, and mostly it's gonna be playing with higher order functions. I think writing a memoized function or like a memoized func is one of them. So there's the answer. Incidentally, this doesn't quite work. One problem with this is that args is a array, and maps treat each array as like a unique thing. So this, because they compare along strict equality, so 1, 2, 3 does not triple equal 1, 2, 3, and that's a problem here. Again, most functional programming languages don't do that. They actually treat two things that are structurally equivalent as being equivalent. And you can use, there's various solutions here. One is to use like an immutable map, which works in this way. Unfortunately, a mutable map is a library. It's part of immutable. Oh, which is actually the last thing I want to say. If I haven't talked about it before, now is the moment. Immutable data structures are pretty common, or like, in fact, sometimes the only type of data structure in functional programming languages. In any case, they're pretty useful. So in an immutable data structure, for example, if I have a list and I call push, so this is an empty list, and if I call push on it, 3, this actually returns a list of 2, 3. Again, I'm using array notation even though these aren't really arrays. I don't know why I'm doing that though. And the immutable list data structure gives us all sorts of other cool things, right? So we can do like list, or let's say we have an immutable map of, let's see, foo. I really don't want to, I want to stop using these metasyntactic variables. They're pointless. But I can't think of anything other than apple, banana, tofu. There's a update in function that lets us say like apple, banana, tofu, and then pass in a mapped function that basically means it's going to like dig down into the data structure and call this on the current value. So that'll be ultimately a map that's like apple, banana, tofu. You might be thinking, gosh, these would be useful in reducers, and they are useful in reducers. Okay. So this is prior immutable. All right. That's it for functional programming. That's all there is to know. That and monads, which I still don't actually know how to talk about monads. I'm not completely clear on the definition of them myself. Yeah. Yes, although the one from last week didn't. Oh, actually, no, that's not true. Yes, I can. All right, great. So we have to stop streaming.